Okay. So, good evening, students. Am I audible clearly? If you can unmute and answer. Hello. Hello. Vinod, am I audible clearly?
This is for VG much negative.
Sorry.
Okay, so what is going on?
Sorry. Hello. Are you saying something? Okay, I'm audible clearly. The screen is visible, right? Okay. So, we'll start in few minutes. So, let others also join. Okay, so it's already 6:05. Maybe we will start. Others will join slowly. So, good evening, everyone. I welcome you all to week 12 of problem solving session. In today's session, so since this is the last session, so we would be wrapping up this analog electronic circuits course live problem solving session. But before that, we will have another session next week. It is basically a summary session, and also we can go with some doubts. If your people have any doubts, we can clear those doubts in that particular session. So, with that, maybe we can start today's session. So, if somebody could confirm, like, am I audible clearly? And is my screen visible to you properly?
Yes, ma'am.
Okay, so let's begin today's session. Just in case if you feel there is some disruption in audio or in my if my screen is stuck, please let me know. And also, if you have any questions, rather than writing them down in the chat, please unmute yourself and interrupt me at any time you feel like. Okay, so with that, let's start solving the problems for today. So, this is the first problem that we have. Here, this particular circuit is a conceptual schematic of a voltage regulator. So in this circuit, this voltage regulator part is the Zener diode. Okay, so Zener diode, we all know Zener diodes are used for voltage regulation, as these diodes are used in reverse bias, where when they approach the breakdown, the voltage is fixed while the current increases. So if we talk about how the profile looks like, so we plot. So the current will rise still certain point. We call this VZ, that is inner voltage, and after that the current increases almost exponentially. So this is how the profile of Zener diode looks like, where the Zener diode is always used in reverse bias. So now this particular circuit of voltage regulator is used. So there is a dirty supply with ripple and noise is regulated into a clean supply. So as you mentioned, dirty supply is the supply voltage with some noise factors, some regularities. So this particular circuit is used to clean that supply, because we know all the circuits, whatever circuit you use, whether in digital or in analog, you would need supply voltage. And many of the times, because of this dirty supply, a lot of error comes into picture. It can also damage your circuit. So that's why it is very important to have a clean supply. And for that purpose, these kind of circuits are used, where the dirty supply from the mains is first cleared, and then that clean supply is provided to your circuits. Okay, so this particular circuit, where we are getting clean supply from the dirty supply, it is given that op amp has a gain of, this is of op amp. Okay, op amp gain is 1319. Again, this is volt by volt gain. R1 and R2 are 19K and 23 kilo ohm resistors. Assume that the op amp has an output resistance of 399 kilo ohms. So here there is an output resistance, we all know, in the op amp. Considering that this is my output resistance, the value of which is 399 kilo ohms. Okay. So the question arises, what is the output resistance of the complete voltage regulator circuit given ohms? So by output resistance, we mean what is the Z out, the equivalent Z out over here is what we want to calculate. Okay. So as we know, okay, so when this is a circuit and we want to find the output impedance at this particular node, the easiest method that we use is, let's say we apply a voltage Vx and a current is flowing Ix through it, such that my Z out that I want to calculate would be Vx upon Ix. Correct? So this is how we solve these kind of problems, especially when we are asked about terminal resistances. So now here, if you observe very carefully, first of all, there is some input current which is going into the op-amp, and there is another current which is going through this path of R1 and R2, right? So let's say I name this one I1 and the other one is I2. This I1 and I2 are such that Ix is summation of I1 and I2. Now, here, since this is an op-amp, we know for an op-amp, the gain is, the output is always gain times, let's say this is A naught, okay? So A naught times into VD. VD is difference voltage. So VD is V plus minus V minus, correct? Now, since we are applying this voltage Vx over here, so considering there is zero voltage here, so how would my VD look like? This is V plus minus V minus. At V plus, if you observe carefully, we said that since there is no voltage applied here, we are saying that it has zero voltage. So that brings us to 0 minus VI. So V minus. V minus is the voltage at this particular node. So that is basically the voltage across this R1 resistor. So how do we write this voltage? So R1 upon R1 plus R2 into Vx. This is Vd, correct? Now if this is my Vd, if this is Vd, then my Vout is A times Vd. So my Vout would be minus A naught R1 by R1 plus R2 into Vx, right? Okay, so this is V naught. Now, if I have to ask, where is this V naught appearing? So, where is the V naught? V naught is basically at the output of the op amp, right? So, here you have your V naught. Okay, so this V naught, now we said that here we have I2 and this is I1. So, if I have to find my I2, how would I write my I2? I2 is basically V naught upon R naught, correct? The output resistance of our op amp and output voltage of the op amp will give me the output current. So my I2 becomes minus A naught R1 upon R1 plus R2 into R naught Vx, right? So this is my I2, that is one of the two currents. Now, when we have the second current, I1, this I1 current is the current that is flowing from R1 and R2. Here, there won't be any current because op amp's input cannot have any current. So that's why I1 would be Vx upon R1 plus R2. So this is the total current through the series resistance R1 and R2. Now, we know Ix is I1 plus I2, that is Vx upon R1 plus R2 plus minus A naught R1 upon R1 plus R2 into R naught Vx. So Ix equal to Vx 1 by R1 plus R2 minus A naught R1 upon R1 plus R2 into R naught. So if we further simplify this, this will become R naught minus A naught R1 upon R1 plus R2 into R naught. Now we know Z out would be Vx upon Ix. So from here, Vx upon Ix, that is Z out would be R1 plus R2 into R naught upon R naught minus A naught R1. Now here we know that R naught is 399 kilo ohm, right? A naught into R1 would be how much? It is 1319 into R1 is 19K. 1319 into 19K. So by this relation, we can clearly observe that A naught R1 is much greater than R naught, right? So we can further simplify this and we can write Z out as R1 plus R2 to R naught upon A naught R1. So there is no point of having a negative resistance. So that's why we are taking mod. So now if we substitute by substituting all these values, the expression or the final result that we obtain is 658.21 ohms. So the Z out turns out to be 658.21 kilo ohm. Any doubts in this?
Uh, yes, I have a doubt in this. So when we have considered the output side of the amplifier
Mm-hmm.
op amp, uh, so usually a voltage dependent voltage source is also there, right? Why haven't we considered it? So that R 399K is the R out, but
Yes, yes.
there should
So,
be.
okay, so I have not, so this is not the complete picture of output side. I have just represented just to show that, okay, there is a resistance. We all know there would be a resistance, right? So, to show that resistance only, I have made it like this. Otherwise, so it's just a pictorial representation, but it's not the complete picture. It's just, okay, there is a resistance present for our analysis. That's it.
Yeah, so wouldn't the analysis change if we include the voltage dependent voltage source, let's say, which is A into VD, right? So that should be the A naught into VD. So I mean the current would be then
Acha,
V.
this will be. So basically, here what you are trying to say is, rather than just this, you mean to say there would be this with A into VD
and then R naught, which is 399K in series with it.
AVD, and there would be this R naught, which we are considering,
Yes.
right?
Yes.
Okay. Okay, so what you're trying to say is you are saying ki the current I2, you would like to write it as A into VD minus VX upon R naught, something like this. This is what you meant?
Yes, like something like that.
Something like this. Okay, so for suppose if this is the scenario, then how things will change. So if this becomes I2, then the value of I2 will change from AVD will remain as it is. So R naught upon R1 plus R2 Vx minus Vx whole by,
I2 would be okay. Yeah.
right?
I2, yes, I2 would be negative of this, right?
Huh. Negative of this. So here, since we have not considered mod yet, so negative will also appear. So this will become A naught R1 by R1 plus R2 into R naught plus 1 by R naught into Vx. So in that
Mm.
scenario, I2 will become minus.
So the second term will be minus inside the bracket.
Whole minus I have taken out. So one minus is coming from here, another minus is here, right? So this is
Uh,
minus Vx, and we will have. Um, So if that is the scenario, how things will change, so we can see like how much is the effect, and according to that we can comment. Okay. So yeah, if this is the scenario, then I2 would become minus Vx A naught R1 plus R1 plus R2 by R1 plus R2 into R naught, correct? Now here also, if you observe, A naught into R1 is 1319 into 19K, correct?
yes,
R1 plus R2 is how much? It is 19 plus 23,
20.
correct? So
Yes,
overall it is
A not R1 only.
yeah. So now here also if you observe 42K is much less than 130 1319 times of 19K, right?
Yes.
So at the end here also it will be approximately minus Vx A naught R1 upon R1 plus R2 into R naught. So you come to the same conclusion,
Okay.
right? So yeah, that is the scenario. Now um, let's move on to the second part. Okay, so one thing if you observe over here very carefully, so if I may write, right, Z out is R1 plus R2 by R1 into R naught by A naught, correct? So I can represent it as R naught by A naught into beta is Z out, where beta is R1 upon R1 plus R2. So this reduction of output resistance, uh, this comes from the negative feedback that is present in this problem. So we discussed that negative feedback stabilizes the gain, right? It reduces the gain to increase the span of your input, correct? To increase the bandwidth of your circuit. Similarly, it also reduces your output resistance, which is one of the requirements that we discussed, right? For the amplifier, like depending on the type, but if it is a voltage amplifier, you definitely want your output resistance to reduce, and that has been obtained by using a negative feedback. So this is one of the advantages that you observe because of negative feedback. Okay, now in the same circuit, so this is question number 2. So, and this is because of negative feedback. Right, so this is an insight that can be driven from the problem. Now, coming to the second problem. So in this problem, again, we are going to use the same circuit. In the same circuit, if the ripple output, if the ripple on the dirty uh, power supply, the output allows the ripple through with the gain of minus 29 dB. So this is the gain of output. Ripple gain is 29 dBs. This is called the power supply gain. Assume that the voltage across the Zener diode is constant and does not change even with the ripple on the power supply voltage. What is the power supply gain of the complete regulated circuit? Now see, if there was no feedback, it is said that this regulated gain power supply um, okay, the power supply ripple gain of this circuit is minus 29 decibels. Now, when there is a negative feedback, we already know Z out dash would be, sorry, G out dash would be G out upon A naught into beta, correct? So, because of this negative feedback, the gain would again reduce. So, when the gain reduces, you would see that. So earlier this 29 minus 29 dB's gain, when you take the antilog of this, the G out comes out to be 0.0355 volt by volt. So this is the gain for the ripple earlier. Now after feedback, I should say after negative feedback, the gain G R dash should become 0.0355 by 1319 into R1 upon R1 plus R2. So that is 0.0355 1319 19 by 42. So the gain value turns out to be 0.0000595 volts by volt. And if we represent this in dBs, so it will become 20 log and in dBs it is minus 84.515 dBs. This is the answer. Is this clear? Hope this is clear. No doubts, right? So now moving on to this next problem. So in this problem, we have the circuit where the inductor and capacitor are so large that the current through the inductor is constant and the voltage across the capacitor is constant. The MOS device has to be in saturation. Vg is given by Vt plus VGST, where given that VGST is 0.15 volts. The power supply voltage is 1.9 volts. Power supply is 1.9 volts. R is zero point 0.9 kilo ohm, zero point 0.9 kilo ohms. And okay, these are the givens. Now, what is the maximum amplitude of VD, this point, such that the device is in saturation, right? So, here we have to find this VD, the maximum amplitude, or basically the maximum value of VD that can appear across this point. So if you observe very carefully, this VDD is actually dropped across this whole circuit as VD drop plus VDS drop, right? The drop across the transistor. And I'm saying VD, basically VD is the drop across this inductor. So this small VD is basically that. So this VD is basically VDD minus VDS. We know VDD is fixed. To get VD max, how do we get VD max? By finding VDS min. Correct? Is this clear to everyone? This is how you would get the maximum value, right? Sorry. Okay. So, the first task is to find VDS min. Now, how do we find VDS min? For saturation, we know VDS should be greater than or equal to VGS minus VT. Right? Now, here we know that for VDS min is equal to VGS minus VT. Here VGS is VG, so this is VT plus VGST minus VT. These two cancel. So VDS min turns out to be VGST, that is 0.15 volts. Now we know VDD is 1.9 volt. VDS min is known to be 0.15 volt. Then we can find the maximum VD, right? So maximum VD will be 1.9 minus 0.15. So which brings us to a VD max of 1.75 volts. So this is the maximum value that can attain at the that can be attained at this point VD, such that your transistor is also in saturation. So the saturation is maintained. This is clear, right? This is very easy. Any doubts in this? Okay, so I hope there are no doubts because this is straightforward. Now, for this same circuit, for the same circuit, while the amplitude of VD is maximum, that is VD max has been used, 1.75 volts. So for this VD, what is the maximum amplitude of ID such that the device is always on? So ID is this current. So ID is the current that is also flowing through R. So if I have to find ID max, I can write it as VD max by R. So this is 1.75 volts by zero point 0.9 kilo ohms. So the value of ID max that we would obtain is 1.944 milliamperes. So again, this is a straightforward problem. Now moving to the next problem. So this is question 4. So okay. So this is question number 5. Again, we are going to use the same circuit. So in this circuit again, we have like we have to assume that the small ID is equal to GM into VG. So the small ID is GM into VG, even for large amplitudes. What is the required value of GM such that the maximum ID is achieved when the amplitude of VD is sorry sorry okay, so we have to find the maximum, we have to find this GM such that we obtain maximum ID and maximum VD is there. So it is given that ID equal to twice of GM into VG. We also know GM equal to 2 times ID upon VOB, right? And from above, we already knew that ID is 1.944 milliamperes. V overdrive is 0.15 volts, that is VGST. So from here, the value of GM turns out to be 2 into 1.944 milliamperes by 0.15 volt. So the value of GM turns out to be 25.926 millisiemens, right? Okay, so now moving on to the next problem. So in this problem, it is given if ID is K times VGS minus VT whole square. what is the corresponding value of k required for the device. So we know that ID is 1.944 milliamperes and ID is also equal to K VGS minus VT whole square. This VGS minus VT is 0.15 volts. So when VGS minus VT is 0.15 volts, so value of K becomes ID by 0.15 whole square. So the value of K turns out to be 86.4 millisiemens per volt. Is this clear? Is
Ma'am,
this clear?
I had a doubt in question number 2, ma'am.
Question number two. Okay. Huh. Yes.
The step where you got G out as 0.035,
Huh.
uh, you took antilog of minus 29 dB. Yes.
Yes, yes. Antilog of minus 29 dBs.
While I was calculating, I got 0.012 round. Ma'am.
Was the
Uh,
problem same?
yes, ma'am. This problem just now
Oh,
while I was
just
solving
now. Okay, okay. So, what you are getting? You are getting
0.00126.
0.00126.
Yes, ma'am.
Oh, okay. So, what about others? Did anyone else also calculate this? Maybe I will try once again. Did anyone like
I'm getting the same 0.0355.
0.0355? Okay.
Yes.
One student got 0.0355, one student got 0.00126. What about others?
Yeah. So 0.0126 would be when we take 10. So it's 20 log because it is volt by volt, right?
Yeah, yeah.
Uh,
Gain would be
so
20 log only.
yeah, 20 log of the voltage gain. So if you take 10 log of this thing, then in that case we are getting 0.0126.
Okay, so can you check once again?
Yes, ma'am.
Yeah, so maybe you can quickly check and revert back.
Yes, ma'am. I got it.
Got it? So were you using 10 log?
Yes, ma'am.
Okay, okay. So no, you have to use 20 log. 10 log is only used in the case of power. When you have power gain, you are talking about power, then only you will use 10 log. Otherwise, you would always use 20 log. So be it voltage gain or current gain, any kind of gain, you would use 20 log. Only for power gain, you will use 10 log. So yeah, you can keep that in mind. Any other doubts? Okay, no doubts in the problems we solved right now, right? So let's try out some problems on transfer functions and Bode plots, okay? So let's take an example. Example one. Let's say my transfer function is So this is the first example. We are going to draw the Bode plot for this. So how do we draw the Bode plot? You would have two x's. Right. So can you tell me what are the two axes? What do these two axes denote? We have discussed it earlier, right? So what does this first axis denote? The vertical axis?
Magnitude.
Magnitude, right? Or gain. So what is the unit of that gain in Bode plots?
dB.
Yes. So make sure your Bode plot is always present in dBs. So vertical axis is dB. What about the horizontal axis?
That's frequency.
Frequency. Here you can have frequency as well as radians depending on you. So do you have what is the speciality of this frequency axis?
It's a log. Uh,
Log, right? So this
log axis.
yes. So this would be an log axis, and this complete plot is a semi-log plot. So semi-log plot means one axis is in log, whereas other axis is linear. And when we say log axis, that means it increases by a factor of 10. Okay, so decade plot. So it's like every step is 10 times the previous one. 100K. Correct? Okay, so we have prepared the layout for our plot. Now we have to solve the transfer function, right? So first of all, is there any pole or any zero at the 0 point? Any pole or zero
Mm,
present at 0 point?
no.
No, right?
Uh,
So your plot will start from 0. Now, what is the gain at 0 frequency? That is the DC gain. What is the DC gain of this transfer function?
1000.
Is it 1000 dBs?
No, no, that's just 1000. So,
Yeah. So
like,
T of 0, T of 0 is 1000. This is volt by volt. This is not in dBs. But in your Bode plot, you have to represent the gain by dBs, right? So
yes,
what will be this value in dBs?
60 dB.
60 dBs, correct. So your plot will start from 60 dB. So let's say this is 60, 40, 20, 0, then you can go downwards. Minus 20, minus 60, and so on. Why I'm separating my spacing of these y-axis by 20 dBs? That is
It's
because a
because
pole or zero can introduce a shift of 20 dBs, maximum 20 dBs. So that's why I'm separating each of them by 20 dBs. Okay. But this is a linear plot. So basically, this is the linear axis. So things increase per dB. So one by one only it will increase. So this is not any log plot or any log axis, right? Okay. So your plot will start from 60 dBs. Since there is no zero or no pole, how will your plot look like? We know the rules, right? What was the rule? When there is a pole, it will introduce minus 20 dB per decade. slope. When there is a 0, it will introduce plus 20 dBs per decade slope, correct? Now, when there is no pole or 0, how will the plot look like?
Flat.
Flat. So it will be a straight line. So now let's do one thing. Let's figure out where all the poles and zeros are present. So we see that there is at frequency, let's say this is hertz, and these are also given in hertz. We see that there is a 0 at 10 hertz, correct? So I'm placing a 0 over here. There is a pole at 100 hertz, again a pole at 1000, a 0 at 10,000, and a pole at 100,000, right? So, okay. Now, we know that from 0 to 10 hertz, there is no pole, no 0 present. So the 60 dB's gain will continue as a straight line. Now, at 10, it encounters a 0. So if it encounters a 0, then 0 के साथ what will happen? It will experience a 20 dB per decade slope, right? Which is a positive slope. So the plot will go upwards, and at 100, you will have a gain of 80 dBs. Is this clear? Any doubts in this? No doubts, right? Okay, now at 100, it observes a pole. So how will the graph look like now? From 100 to 1000, how will the graph look like?
Straight line.
Straight
Flat.
line. Flat.
Flat.
Why flat? Because earlier it was plus 20. Now because of pole, it will become minus 20. So the resultant is flat. Correct? Now what happens at 10K? What will happen at 10K?
It will decrease with minus 20 dB per decade.
It will decrease by minus 20 dB per decade. So it will again come to 60 dB per decade. Right? Now what will happen from 10K to 100K?
So it will again go flat.
It will again go flat because of a 0. Now, when will it, after this, what will happen at 100K?
Minus 20 dB per decade.
The slope
Decrement.
is minus 20 dB per decade, right? So this is minus 20 dB per decade. Here it is 0 dB per decade. Here it is minus 20 dB per decade. Here it is 0 dB per decade. Here it is plus 20 dB per decade. Here it is 0 dB per decade. Okay, so now if I ask you at what frequency you will obtain a unit gain, at what frequency you would obtain a unit gain? So what is the frequency at which you would obtain a unit gain?
That would be 0 dB, right? So
Yes, that would be 0 dB. Unit gain is 0 dB. So at what frequency this curve or this Bode plot will cross your 0 dB axis? What is that frequency?
that would be 60 divided by that frequency. That frequency minus 100K is equals to minus 20.
So what is this frequency? That is what I'm asking. What is the value of this frequency?
Um, $300K. Oh no, sorry. 100.
Okay, so see, let's analyze. How would you analyze? Here you started with 60 dBs. At this point you have 40 dBs. At this point you have 20 dBs. And then here you have 0 dBs, right? The slope is fixed. That is 20 dB per decade. So to move from here to here, you would require 1 decade. Correct? Now,
Yes.
to move from here to here, you would again require 1 decade. Correct?
Yes.
Now, from here to here, again you would require 1 decade. Correct?
Hmm.
So you would require 3 decades to reach to 0 dB. You are already at 100K. 100K into 10 for 1 decade, into 10 for another decade, into 10 for a third decade, right? So
Yes.
here it becomes with this 1 mega, right? By introduction of this, it will become 10 mega. By introduction of this, it will become 100 megahertz. So unit crossover frequency, that is 0 dB frequency, is 100
Megahertz.
megahertz for the given transfer function. Correct? This
Yes.
is clear, right? No doubts. So the question is, why did I ask for unit crossover frequency? Was there any importance of this unit crossover frequency?
Mm,
Do you remember any usage of this unit crossover frequency?
Something like related to phase margin or
Yes.
stability.
Yes. So your phase margin, when you calculate your phase margin at unit crossover frequency. That's why it is very important to identify this unit crossover frequency, because your phase margin now you will calculate at 100 megahertz. At this frequency, you will find the phase margin and see whether your system is stable or not. Is this clear? So how this Bode plot is giving you the stability information? Now from here, you already know that crossover frequency. You will simply find the phase of this transfer function and substitute this unit crossover frequency and see what is the phase margin that you are getting. Is it more than 0, less than 0, equal to 0? Is this clear to everyone? Okay. So now let's change something in this problem, okay? Let's say I have, okay, so let's make it a second, let's make it our second example. Example 2. Okay, so this is my transfer function right now, right? So first of all, what is the DC gain? A naught. The moment you see the transfer function, be it in any form, try to bring it to this particular style of form. Okay, when you bring your transfer function to this form, it is very easy to analyze things. Like you can pick your poles and zeros just by looking at the transfer function, and you can also comment on the DC gain. Now, other than this, let's say if I would have written my transfer function as 100. Right, so I have this transfer function 1 and 2. So can you tell me, are transfer function 1 and 2 both same or different? So are T1 and T2 same or are they different? And if they are different, how they are different?
Do we have this S as well in T2?
Yes, the S is same. Okay, so acha yahan pe na. हाँ, yes, the same as. So are poles and zeros at same position in both T1 and T2 first of all?
If we take the second term out from all of them,
What do you mean by
uh,
the second term?
like again convert it into this thing, the T1. So S plus 10, so we can write, let's take 10 outside and S by
I
10
mean,
plus
see,
1.
if S plus 10 equal to 0, then S equal to minus 10. If S by 10 plus 1 equal to 0, then S equal
S
to
is equal to minus
minus 10,
10.
right? So in both the
Yes,
cases, you are getting the same values, right?
yes,
So poles and zeros are at the same position, right? There is no change in them, correct?
yes.
So in that sense, both the transfer functions are similar.
Mm.
Agreed?
Yes.
What about the DC gains?
Um, so that be different.
Is it same or different in both the cases?
Um, it is different.
Okay, so why would you say that it is different? If you can comment.
So if we take 10 out, I mean, sorry, the second term out, let's say, convert it into a standard form, uh, the second function into
Mm-hmm.
as a form of first function,
Mm.
then in that case, the, I mean, we will have a factor of 1 by 10k, I guess, in the denominator.
Acha, so let me simplify your question, okay? So my
Mm.
question is, tell me the value of A10, A20. That is DC gain of transfer function 1 and DC gain of transfer function 2.
In this case, it is same. Like 0, we are getting 100. If we put S is equals to 0, we get 0 for both T1 and T2.
Will you?
Yes, S is equals to 0. Yeah.
Okay, so here because of this S, no? Let's say
Yes.
I remove this then.
Oh, in that case, we'll have mm, no 100. Yeah, in that case, we'll have a different this thing.
Okay, somebody says it will be 100 and 0. Can you explain why you are saying that? So one case is 100. So you mean transfer function 1 will give you 100 gain and transfer function 2 will give you 0. I guess it was Vinod. So can you unmute yourself and answer Vinod? Why it is 0 for the second and 100 for the first? Okay, so let's analyze. See, when we
It is
say
different.
it is different, but
Yes.
what are the values? Is it
So
0?
in the second no, it's not 0. It's
Hmm.
100 by 100 100k 100 by 100k square. Like
So basically, the
so.
idea is whenever you are asked to find the DC gain of a transfer function, only thing that you have to do is you put S to 0. You substitute S to 0 and then you will find the DC gain. Now, in first case, when you put S to 0, you see your gain comes out to be 100. Right? Everybody can see this? In first case, it is coming
Yes.
0. Now, what about
Yes.
the second case?
It's 100 by 10k.
So it is 100 into 10 that is coming from here. From here it is 10k square by 100 into 1000 square into 100,000. Right? This 100 cancel. So here it is 10k, 10k and 100k cancel. This is 10, so this will be 100. So your E2 of 0 turns out to be 1 upon 100k. Is it,
So there is a 1k at the top. So
then
when we
take
cancel 10k into
100,000,
10k,
right? Still 1,000 is left. So it will be 100, 1 by 100. So 1 by 100 is the gain that you obtain from T2, right?
yes.
Now from here, while looking uh, in the beginning, you could say that okay, my poles are at same position, my zeros are at same position. But when you have to start your Bode plot, where would you start the Bode plot? After analyzing your 0 dB gain, that is your DC gain, you can clearly see the difference, right? In this case, your graph starts from, yes, what is the value in dBs here?
Uh, 40.
Yes, it is 40 dBs. What about in this case?
That would be minus 40.
Yes, it is minus 40. You can clearly see the difference, right?
Yes.
In both the cases, your graph is starting from different point. So when your graph is starting from different point, so its poles and zeros, according to them, your crossover frequencies will be different, right?
Yes.
There might be a possibility that the second one, which is starting from minus 40, it might not come above 1 dB. That is also true.
Right.
So the gain might be always negative, right?
Mm.
So that's why
Yes. True.
it is very important to analyze your circuit and to analyze your transfer function. And the best practice is to bring your transfer function to this format. Why I suggest you bring your transfer function to this format is because from here you can clearly see your DC gain. You don't have to compute this much. You can clearly see this is your DC gain. So the moment you bring your transfer function to this format, it is easier for you to analyze the things. Am I clear to everyone?
Yes.
So yeah, now that is one learning. Secondly, let's say example 3. My transfer function is 100s s by 10 plus 1 s by 10k plus 1 whole square. So I'm repeating the same previous transfer function. So now for this particular transfer function, let's draw the Bode plot, okay? So say so it's my 20, 40, 60 minus 20 minus 40. Right? Now here, first of all, tell me where are my poles and zeros. So where are all my zeros? What is the location of my zeros?
0,
Hmm.
then 10
Hmm.
and 10K.
10k. How many? Is it single
3.
zero?
Sorry, two zeros. 10K, 10K.
Two zeros, right? So it's very important to also see how many zeros. So similarly, what about
100.
poles? 100.
100. Oh, so this is repeating the second one.
Okay, so
That is
here
1000.
1000, right? Yeah.
Then 1000,
Hmm.
and then 100K. 4 poles.
So you have four zeros and four pole system, correct?
Yes.
Now, with this information, let us begin drawing the pole zero diagram. So first of all, we have a zero at 0. So you have a 0 at 0. Then you have a 0 at 10. What about 100? You have a pole. 1000, you have two poles. 10,000, you have two zeros. And 100,000, you have a pole. Correct?
Yes.
Now, let me extend this so that we have a clear idea. Okay. So our graph is starting from 0, and you have 100 dBs of DC gain. So 100 dBs means how much in, 100 volt by volt means how many dBs? 40 dBs.
That is 40.
So your
Uh,
graph will start from 40 dBs. You
so
have,
I have a question in this.
yes.
So when we keep S is equals to 0, so the whole transfer function goes to 0. So is there an exception in this case? Like we
Uh, okay. So in this case, so ideally, what you do is your transfer function never starts from 0, 0. So it's very small frequency, right? When you are seeing that it is increasing by decades, so from there you can understand that you will never see a 0 in the scale, right? Before 10, you will get a 1, then you will see 0.1, 0.01, right?
yes.
So we can understand that we are starting the graph from 1 hertz frequency, right?
Okay.
And since it is 1 hertz, so we can see all like 1 by 10, 1 by 10K, 1 by 100, 1 by 1000. These are very small values. So
Right.
we can neglect them, right?
Yes.
The reason being that this graph never starts from 0, right? So that's
Right.
why we are starting it from 40 dBs. Okay?
Uh, yes. So that
Now,
means whenever we have a that means whenever we have a zero or a pole, like simply
yes,
like S
at origin. At
at
origin,
origin,
when
yes.
there is a 0 and a pole, the things slightly change because we know the moment you will substitute s as complete 0, in case of 0 your transfer function will go to 0, in case of pole your transfer function will go to infinity. So at
Right.
that time it is very so you, how would you define your DC gain? There is no chance, right?
Yes.
So for that purpose, we can see, and also from if I have to talk technically from the Bode plots perspective, also we are reducing the plot by a decade. So there is no chance that you can obtain a 0 in this plot, right? Like exact 0 value, because it is reducing
Yes.
by decades. So from that also you can understand it. So that's why we are starting in from 40 dBs. Okay? Is this clear
Right.
to everyone? This is something very important. So yeah. Now you are starting this from 0 because of this 100 that is present over there. And we also know that there is a 0 at 0. So when there is a 0 at 0, then how will your slope look like? It is 20
Plus
dB per
20
decade.
dB.
So 20 dB per decade. So that means at 10, your gain will increase to 60 dBs, right?
Yes.
And again, when you have at 10, there is another 0, right? So
Yes.
earlier, the slope was 20 dB per decade. By encountering another 0, what will the slope look like? How will the slope change?
Another plus 20, so that means 40 dB per decade.
40 dB per decade. So what will be my gain at this point?
60 plus 40, 100.
So here it will be 100 dBs, right? Because this is
Yes.
plus 40 dB per decade. Here you have 20 dBs per decade. Is this clear to everyone? How we are, how we have arrived to this conclusion? Is this clear to everyone?
Yes, ma'am.
Okay, so maybe I'll extend the graph only so that. Okay. So now we have come across two zeros and one poles, right? And okay, so at this point you encounter a pole, right? At this point you are encountering a pole at 100. So what will happen to your slope?
It will be 40 minus 20, which is 20 dB per decade.
Yes, the slope will become 20 dB per decade and you would reach
120.
120, right?
Yes.
So here it is 20 dB per decade. Now at this point, at 1000 you have two poles. So when you have two poles, how will your transfer function change? Earlier it is plus 20. Now your graph becomes,
Minus
slope
20.
becomes minus 40. So the resultant is
Minus 20.
minus 20. So the gain will come down to how much?
100 again.
So this will be 100 again. Right? So at this point you have 100. Now at 10K you have, okay,
2 zeros.
you have two zeros. So at 10K if you have two zeros, so first of all the slope will increase
Increase
by
by plus 40.
plus
Plus
40
40 dB per decade.
per decade. So currently what is the slope?
Minus 20.
And yours, okay, so currently it is minus 20. It is going to increase by plus 40. So the resultant will look like how much?
Plus 20.
So it is plus 20. So again you would reach
120.
120 and here you have plus 20 dBs per decade. Now at 100K you are obtaining a
Pole.
pole. So what will happen to your Bode plot?
It will flat. It will be flat.
It will be flat because of plus 20 and minus 20. So this curve will now continue till infinity, right?
Yes.
So is there a zero crossover frequency present?
No.
So there is no zero crossover frequency for this particular transfer function. So if there is no zero crossover frequency, then what about the stability?
We cannot find out about the stability or
Okay, so what happens is when your curve crosses your when your curve crosses the this 0 dB path, after that the system almost becomes unstable. But
it is stable in this case.
so yeah, it is stable in this case. because if you observe the system, mm, at the end you have a pole, and so it's more like a single pole system. So if there was a single pole system, if it is a single pole system, then we said that it is stable
Always
as
stable.
it crosses almost at infinity or very high frequencies. Or either it is a one pole one zero system, then it is stable. So it is basically because it does not cross your zero crossover frequency. So as it does not crosses the zero crossover frequency, your curve will look like this. Okay, so this is one example. Now,
So can we say like if any like at the end if the board plot flattens out, so it will always be stable, either in like plus dB or in minus dB,
uh, I mean, more or less, yes.
because we are not having, I think, can this be intuitive that the gain is like
Because
stable kind of,
see,
we
here
don't.
if I start writing the phase, how will my phase look like in this particular system? If I have to write the phase of the system, how will my phase look like? So phase, because of zero, I will get 0 degrees plus tan inverse omega by 10 plus tan inverse 2 tan inverse omega by 10k minus tan inverse omega by 100 minus tan inverse omega by 1000, so 2 tan inverse minus tan inverse omega by 10k, right? This is how you would write the phase for the system, correct?
Yes.
So now when omega is at infinity, so that the crossover is happening at infinity, right? Because it is parallel, so it will go to infinity. So tan inverse
Yes.
infinity is how much? 90, right?
Mm.
So it is 90 plus 180 minus 90 minus 180 minus 90, correct?
Yes.
So if I have to nullify them, what is the phase that I am getting?
Minus
Minus
90.
90 degrees, correct?
Yes.
So phase margin is 180 minus the phase, correct?
Mm.
So the phase margin that you obtain over here is
90 degree.
90 degrees, right?
Yes.
Which is more than zero. So the system is
Stable.
stable.
Yeah. So I just meant like intuitively, even from like the board plot, because I mean, it should, the gain or the transfer function should always have some finite value, right? It should not go out of bound. So
Yeah.
here, I mean, we are getting a finite value of 120 dB throughout after, I mean, at the end.
Huh. Huh.
So it should be stable. I mean, this is
Yeah.
intuitively I'm saying.
Yeah. Yeah. From that also you can say. So you are saying that suppose at the end I would have got this plus 20 dB per decade ka slope, and it would have
Yeah.
been continuously increasing. So
Yes. So that would be out of bound.
if that would have happened, then what would, so basically what that means is the pole at 100k is not present. That is the scenario, right?
Yes.
So if one pole is not present, then your phase margin becomes
So that 100K would go away. So that would
100k
be
would go
zero,
away,
zero,
so that would be
zero,
0.
zero.
So 0 हो जाने से your phase margin, you are getting a phase margin of 180 degrees.
Mm.
So, but when we say that phase margin of 180 is still a phase margin, right? So, from phase margin's perspective, it is stable, but from gain's perspective, it is
Uh,
in concept, it is stable, but technically speaking, the gain is continuously increasing by a uh, value of 20 dBs per decade.
but that is
Mm.
unbound, right? It's kind of unbound system.
Gain becomes unbound in that case, no? Practically speaking, if we talk from practical terms, there it becomes unbound. But from physically, like from formulas and everything, it is still a bounded system. Hmm. Yeah, I mean, you can have those kind of systems. The thing is, these are just examples, right? Will they be practically used or not? That is a different story. Like, will these uh, transfer functions, so are there real life systems or circuits which exist that can have these kind of transfer functions? Is a different story. It's just to analyze, like, how would you analyze your transfer functions? For that purpose, we are doing these problems. But I get your point where you are coming from. It's like, so your question is that, let's say I have, yeah, so I have this only and it is continuously increasing like this with the slope of 20 dB per decade. So when this is the scenario, then definitely for infinite frequency, this will reach infinite gain that is there. So will we call it a stable or unstable system? So we have observed that from the phase margin perspective, it is stable. Like from phase margin formula, this particular system is stable. Practically speaking, mm, it becomes unbounded. How would we say this? So is this a stable or not? That's a good question actually. So it's so that is what, so sometimes
Sorry, we can't hear you. I mean, I can't hear you.
Yes, ma'am.
Okay. So now I am audible, right?
Yes, ma'am.
Okay, okay. So at
Yes.
what point did my audio cut off? So where were we? So yeah, basically we were discussing that when that kind of scenario happens, like if it is extending infinitely, so definitely at infinite frequency the gain becomes infinite. But when we saw that from phase margin concept, from phase margin concept, it gives us a stable system. But talking from a practical perspective, definitely infinite gain is something that is unbound, but still like we still have the viable range to use, right? How long would you go? You can go to, like, let's say 100 gigahertz, the operational frequency. Until that, you are still having some finite gain, right? It's not completely infinite. So you can still say that it is a bounded system, but yeah, so it's somewhere it's more like a gray kind of situation where you have, so it's stable and also unbound at the same point. So it is somewhat of that kind. So yeah, that is something. But anyways, so the thing is, would you have these kind of systems or not? So the answer is, whenever we are designing some systems, we focus on number of poles. We also try to minimize number of zeros, because it's more like zeros are not much of use to us. It's just when we have to compensate, we try to introduce the zeros, but rather we want to have only pole based systems. And also the idea is that in your system, number of poles are always greater than number of zeros. So it is observed practically that all the systems that are designed, the number of poles are always greater than number of zeros. So when that is the scenario, you would never get this kind of behavior. You would always either come to this constant behavior, that is, it becomes constant through infinity, or else you would see a decreasing slope. But you would never come across this like increasing uh, increasing transfer function. You would never see that or never encountered that, because in practical life, the systems which are formed out of your electrical components and everything, whenever you try to introduce a zero, it somehow introduces a pole. So a zero always comes with a pole. So that's why your system is always pole heavy system, or there might be a chance that your poles and zeros are balanced, but you would rarely see a zero heavy system. That means a transfer function, practically speaking, like in practical systems that you have, that your zeros are like the number of zeros are more than the number of holes. So that rarely happens. But yeah, that was a good discussion. That is something that we can think of. So yeah. So, anyways, you understood this, like how to deal with uh, poles and zeros in a Bode plot.
Yes.
Okay. So there is another kind of example that can be introduced. So another thing is like, let's say if we have the similar transfer function, but instead of pole, sorry, instead of a zero at uh, instead of a zero at zero, you will have a pole at zero. So now, if that is the scenario, how will your transfer function change? So okay. Yeah, right. So when this is the scenario, again your graph is starting from 100, that is 40 dBs. But first you encounter a pole that is at 0. So because of that, you will have a 20 dB per decade slope, that is minus 20 dB per decade slope. Now at 10, you experience a 0, so it will make your system flat. After that, at 100, you have one pole. So at 100, you have one pole. So this becomes plus 20 dB per decade. Now here it is minus 20, minus 40. Now when you reach 1K, you have two poles. It becomes minus 40 dB per decade. Now at 10K, you have two zeros. Oh wait, so this was minus 20. Here it was, so that should be minus 60, right? Because at 100 you already had one pole. So this will be coming down to here because minus 40 plus minus 20, so it's minus 60. Now when it comes to 10K, you encounter two zeros. Two zeros, so your slope now changes to minus 20 dBs. So it is minus 20 dB per decade. Minus 20 dB per decade. Here it was minus 60 dBs per decade. 0 dB per decade. This is my crossover frequency. And here, when it reaches minus 80, then again at 100K, there is another pole. So it is minus 100, minus 120. So until it reaches this point, so here the slope becomes minus 40 dB per decade. So did you see how things have changed? Like just by interchanging the pole and zero at the zero. So earlier there was a zero at zero. Now there is a zero at pole. But you can see the transfer function has completely changed. The Bode plot has completely changed. And now you can clearly observe the crossover frequency. So UGF, that is unity gain frequency, right? So this is how your plot changes. This arrangement will also change based on where your poles and zeros are. So based on your pole zero arrangement, your this Bode plot will completely change. So is this clear to everyone?
So I have a question. So in any of the cases, when there is a pole or a zero at zero,
Huh.
um, so let's say the first frequency where the change was occurring was at 10 hertz.
Huh.
Uh, so we took like the starting point as one hertz.
Yes.
Uh, if it is like 100 hertz or let's say 1K, 1
Huh.
kilohertz,
Hmm.
so where will we start it from? So will we start a decade lower from that? Okay,
No, no,
until
we'll
then,
start from 1 hertz only. So this is the point where we start, right? So from the starting, because the graph should start from initial only. So we'll start from 1 hertz only. Now, let's say my first pole would have appeared directly at 1000K, 1000 hertz only. Then what I would have done is, like, let's say I'm changing the color. This was my first pole, okay?
Mm.
First pole. Sorry, second pole. This is second pole,
Yeah,
and
second,
here
yes,
I had first pole. When that is the scenario, I know that 20 dB per decade, minus 20 dB per decade slope will be maintained. So that
yes,
brings me to the point that, okay, at this point, I should get a gain of minus
minus
20.
20. Mm.
And this curve would actually follow. So
Right.
this is how it would be, and I will get my so here actually because of drawing there is some problem, but otherwise this would intersect at your 100 hertz, right?
Right. Yeah. But so just general question, why at 1 hertz? Why not, let's say, 0.1 or 0.01 hertz? Is like 1 hertz a standard or
No, no, it's
something?
not like that. It's just that you start your graph, right? So when I'm saying, okay, I'm drawing my graph from 10, 100,000, so the step before is 1, right? If I would have started my graph from 1, 10, 100,000, then the previous one would have been zero point 0.1 only. So it's more like that.
Okay, because I think probably the graph would change in that case. Like if we start from 1 or 0.1,
It would
something
not
like that.
change much because the slope remains same, and you
Yeah,
know that by decades it is. Oh, okay, so you mean to say ki.
the gain at a particular frequency would change, right? And that would change other things.
Right, 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 right. uh, okay, so when that is the case, then things will change slightly, because now when I'm starting from 1 and reaching till 1000, I say there is 20 dB per decade slope, so it is crossing at 100.
Yes. Let's say if we start from point 1, so we'll
Point
reach
1.
one more down, minus 40, right?
Yes, yes, yes.
Yeah.
True.
So that's
That's
what I
true.
meant.
That is true. Mm, right, right. So when that is the case, things will change slightly.
Because accordingly, we'll have a different unity gain frequency as well for all of the those cases.
So rather than uh, other than that, you can directly compute your unity gain frequency from Bode plot itself, right? So you can calculate, like compute for the transfer function's magnitude, and from there you can directly find the omega, for
Right.
which
Okay.
the gain is 1. So
Mm.
वहाँ से you will get the direct value of UGF.
Uh, that would be a tedious method, but yes.
Yeah, that is,
Uh,
that is for the case when, see, when you have constant DC gain, like there is no pole and zero at origin, then things are very easy, because now there things does not change until you encounter a pole and zero. The problem arises when you have a pole and zero at the center, or at the origin, that is zero frequency. There it leads to the problem, right? Because of that slope that will be appearing.
yes. So are there systems that have like these kind of things like poles and zeros at zero? And
Rarely, very rare. Because we
okay.
know that these poles and zeros come from R and C's, right?
Yes.
Pole zero comes from pole or zero. How do you write a pole or a zero? 1 upon RC. And if
Mm,
you write it like 1 upon RC, that means, is there a possibility that in any system you have 0 R or 0 C? That is never possible
no.
practically, right? You can
Yes.
have a completely capacitive system without resistance, or matlab, complete resistance is still true, but there might be some parasitic capacitance present. And vice versa, when you have a capacitor, there might be some parasitic resistance present. So it's never possible to have a polar zero at zero. So it's very rare. Like practically speaking, if we are talking about the practical systems available to us, this is very rare. But
Mm,
still,
okay.
for analysis perspective, as you need to know that how to deal with these kind of systems, so that's why it is important.
Right.
Understood?
Yes. Thank you.
Okay. So any other doubts?
No. Can we have a small discussion on this one if you happen to find someone like where to start from exactly?
Where to start from in what case?
Like so the case we discussed right now, so 1 or 0.1 or 0.01. So
Huh.
is there like a standard method to like or
So you
as
can
some
start
guideline?
from 1 decade before. maybe. So
Okay.
yeah, because you will so it's like you'd be drawing your graph, right? But
Hmm.
when you're drawing your graph, you would place your first unit as a decade apart.
Okay.
Always one unit is
S-
a decade apart, and then all others follow. So it's 1 decade apart, always.
right.
So if
Uh,
first pole or zero is appearing at, let's say, 10, you can start with 1. If it is appearing at 1, you can start with point 0.1. If it is appearing at point 0.1, you can start it at 0.01. So maybe 1 decade ahead.
okay. Let's say anything greater than one, if it is appearing, so we'll always take the starting point as one, like as a guideline.
No, it's
And
more like 1 decade. You can consider it as 1 decade because all these steps are 1 decade, right?
yes, but
So
let's say if
from first point to this point is also 1 decade, no?
yes,
If
yes.
this is 1 decade, others are also 1 decade. So the starting one should also be 1 decade, no, for the uniformity.
It should be, let's say if we have the starting one at then 1K, like in that
Ah.
case, like what would we do?
So
So
if
will we
the
start from
starting one
100?
is 1K, then your graph should start at 100 to maintain this uniformity so that all the slices are equally placed, right?
Okay.
Yeah. But there is no rule as such. But yeah, so just
Uh,
for the
uh,
uniformity of the plot, you can take it this way.
yeah, but even in that case, if we have something at 1K and one pole at one pole at 0 and
Hmm.
the second pole at 1K, so I mean, the slope starts degrading from at minus 20 dB per decade from 0 itself, right? Like 0 or maybe some less frequency, not from 100 onwards.
Right, right.
So,
So,
like,
but where would
there,
you start? Like close to zero
I,
can be 0.001, it can be 0.01, it can be 1, it can be 10.
yes, exactly. But that would
Because
again change
compared to
the,
1,000, it's way too small, right? Mm.
yes. I mean, that would change the unity gain frequency. So, I mean, it would cut out if we look at just the board plot, not just like try to solve it
To solve it
analytically with the
analytically.
equation.
Yeah, yeah. I mean, see, when so it's more like so theoretically you would never experience such kind of problems as far as I understand, just because of these kind of complications, right?
Mm,
So the moment you find the transfer function, you can definitely find the unity gain frequency by substituting the like by finding the calculating the values, and that is the practice always. And alternatively, also, if let's say a body plot is given and you have to find the transfer function, you will find the transfer function based on the poles and zeros. And from there, if it is not in the starting place, like between zero frequency to your first either pole or 0 point, until then it is fine, right? There is no issue. The
yes,
only complication comes when you have like there is a pole or a zero at the beginning, and then you have the first pole or zero, but you find that your crossover frequency has already been met. So in that
yes.
scenario, it's a bit tricky. But
Mm,
thinking from academic perspective, that will never happen because people who design the problems keep these things in mind already. But practically, like, how would you solve this issue?
I
So that's
mean,
what
like,
I'm saying.
let's
So
say,
practically, also, it's very rare. Like, I have never came across a system which is a practical system made up of capacitors and resistors, which can give me a transfer function where I have either a pole or a zero at zero. I never came across them. So that
uh,
is also very rare. So yeah.
the integrators, like that
No, there
S
also
is in,
that is never the case. So when you
Okay.
see the integrators or differentiators which are made up in the system, so you would either use this kind of system. So this is the most easier way, right?
Yes.
So here also, if you see, you would have one R and C. So when you have either R and C, it's never one single system, right? It's always a combination of R and C. So when there is always a combination of R and C, then you will never get a pole that is pole or zero, that is 1 upon RC, to be like R and C can never be zero, right?
Yes.
It will give you some value practically. So this is never possible to have a pole and zero at zero practically. Like at least I have never come across. So yeah, that is the case.
Uh,
Yes. So practically that can never happen.
okay.
Yeah.
Thank you.
Yeah, but that was a good discussion, right? Like
Yes.
sometimes you oversee a few things, but when question comes, it's important to discuss. So yeah, and another thing is now what we did here is we found out like we already had the transfer function. We only drew the Bode plot. There might be scenarios when you are given with the Bode plot. Okay, so you would see
Mm.
some plot like this. Your so the slopes would be mentioned, or you can calculate the slopes based on the values. So all the values would be given, frequency values, gains, and everything. From there, you have to compute it reverse. So you have to find the transfer function from the Bode plot. So that can
Right.
also be done. So if you have some time, maybe we can take one example, or we can take it up next week. So everyone, next week there will be one more session. It's a summary session. So we will. I would basically summarize few concepts that we have already done in these 12 sessions, and that will also act as a doubt clearing session. So if you have if you have doubts or you want to discuss something, please feel free to join. We can discuss your doubts. So again, that session will be held on Monday, that is 21st, if I'm not wrong. Yeah, it is 21st from same time and using same link most probably. Yeah. So 6 to 8, the doubt clearing session would be there next week, along with the summarizing session where I'll summarize the concepts that we have already discussed earlier. So with that, we can end this session today over here, and let's meet next week for one last time before your exam. So when is the exam for this particular subject?
November 2nd, ma'am.
November 2nd, no? Okay. So still you would have time. So you all can come up with your doubts. We can like I'll briefly cover the concepts. So maybe I can take up the notes and we can go through the notes only quickly, and then um, if we can solve this doubt session. So we can have a doubt session next week. Okay, so if you don't have any further doubts, or if you have doubts, maybe we can take up in the next session. So that's all for today. Thank you for joining, everyone.
Thank you,
Thank you.
ma'am.
Thank you.
Thank you, ma'am.
Thank you.
Thank you. Bye.
Ma'am,
Yes.
ma'am, will you please share your number? If I have any doubt, I can able to ask you.
So if you have any doubt, you can contact me through my email. My emails are always mentioned. And also, we will have a doubt session next week. So it's a 2 hour session completely. Maybe half an hour, I'll wrap up the concepts quickly and then we'll take up the doubts. So next week, you
But
can.
I want to make me more familiar with this concept, ma'am, because I'm not still aware of this some of the topics, ma'am.
Okay, so maybe you can go through the lectures. So you have gone through the lectures, you have gone through all these sessions like recordings and everything.
I have attended all sessions, ma'am.
Okay. So, but still there are some concepts which have not been taken up in these sessions that you have doubt with. Is that the case?
Yes, ma'am.
Okay, so are those topics covered in the lectures?
Ma'am, I need to get better idea about this analog circuits, this course, ma'am.
So have you gone through the NPTEL lectures?
Yes, ma'am. Half of the portions I covered, ma'am.
Okay, so maybe you can cover them. And if still there are some topics that, then there is a possibility that those topics might be out of the scope of this particular course. But yeah, if something is like that, maybe we can discuss next week. If it still feels like it's out of scope, so maybe I can suggest you something on that.
Thank you, ma'am.
Okay? Yeah. See you next week.